Hello, everyone. Today, I have the great pleasure of introducing Professor Iyad Masad as our Kant Around the World speaker. Professor Masad is one of the pioneers of the pavement research area, and personally, he's one of the people that I look up to. He's currently a professor in the Civil Engineering Department at the Texas A&M University and the professor in the Mechanical Engineering Program at Texas A&M at Qatar. He's also the Executive Director of Global Initiative at the Texas A&M Engineering Experiment Station, a Fellow of ASCE, and a Fellow of the American Association for Advancement of Science. He is also the recipient of the prestigious James Lowry Prize for 2019 from ASCE. His research interest includes constitutive modeling of geomaterials, micromechanical characterization of the material, and analysis and design of pavement system. In his presentation today, he will be covering the narrow characterization for analysis and design of sustainable asphaltic material. As usual, there will be no question during the presentation. The presentation will be 40 minutes, followed by 20 minutes question and answers. So in order to ask your question, you have two options. The first option is to go to the participant tab and click on raise your hand. The other option is to add your question within the chat, and I'll ask it on your behalf. Without further ado, please join me in welcoming Professor Iyad Masad.
Isaac, thank you so much for this opportunity and for the group, the students who are organizing this excellent seminar idea that is providing connectivity in this difficult time for everybody. So it's not only technical connectivity, but we need it at the personal level to connect with people we know and with our friends all around the world. I want to give special thanks for my friend, Dr. Imad Al-Qadi, Professor Imad Al-Qadi, who's more than a friend. Professor Al-Qadi has been a mentor for throughout my career, so I want to thank him for this opportunity as well. I'll share the screen. So I chose a topic to speak about that is actually, it's even new to me, relatively new to me, but I'm fascinated by it. And we started working on it only a few years ago, but I believe we made enough impact and we have results to share with you. So what it is, it's about how do we use nanocharacterization for analysis and design of sustainable asphaltic materials. So the key in this title is the small scale characterization. What additional value does it offer? Second, how do we use it in analysis and in design of new novel materials that add life to the pavement? First of all, I want to acknowledge my collaborators and students who contributed directly to this presentation, but there are many more students, colleagues, and collaborators who impacted my research in different ways that there is no room to list all of them here, but some of them are watching, and I'm grateful for what they've done through my career in terms of stimulating ideas and being excellent collaborators. So those that contributed directly to my presentation: Amal Abdelaziz, PhD student at Texas A&M University; Muhammad Al-Jarrah, same PhD student; Irina Holleran, she's in New Zealand. She told me today she cannot be watching because it's 2 a.m. in New Zealand. She's a collaborator who comes here and spends time with us in our lab in Qatar. Ilaria Minapache, who was a researcher with my group, now she's back in Europe. And Lakshmi Roja is currently a postdoc in Texas A&M University at Qatar. Before I go into my presentation, I want to also acknowledge the excellent support that I've been receiving to make this research possible, from fundamental research to applied research, namely Qatar National Research Fund, Qatar Petrochemical Company, and they have a consortium of asphalt pavement companies in Qatar, include several companies, local and international companies, that provide continuous support for us, both logistically, materials, and funding, and the Public Works Authority, which is equivalent to the Department of Transportation in the United States. So what I'm doing in Qatar, as Isaac said, I'm a professor in Texas A&M University. Our university opened a branch in Qatar 16 years ago. Now it's about 17 years ago. And I came here 12 years ago to stay for less than a year, but I liked it and I stayed here. And been fortunate enough that we've been able to do major projects in pavements in Qatar, as you can see the list, that goes from road design, materials development, and we've been fortunate that we had the funding that will allow us to do innovative research at the fundamental level. But what I'm also proud of that it's, you know, you have to be in the right place at the right time. And this happened with me being Qatar, when Qatar decided to build their infrastructure, rebuild their infrastructure and develop it significantly. Qatar today is very different than the infrastructure that I found when I came here in 2007, 2008. So I've been involved in various implementation of developing QC/QA programs, upgrading the specifications. So that's been very fortunate that I've been able to move what I know to the practice, and I'm proud of that. In fact, several of my colleagues who helped me on this journey, Dr. Imad Al-Qadi, Dr. Dallas Little, John D'Angelo, and Irv Dokatz, and many who I called upon to help me in this journey to implementing research. But as a professor also, what we've been proud of is we offer annually training programs annually in Qatar. We train engineers, we train practitioners on pavement technology, and all these projects involve students. So that's another value. Okay, so what we're doing in our research is we are addressing the sustainable development goals. So our goal is more than just simply building roads, which is great, building the roads, because as you all know, it adds great economic value. But I wanna remind myself and you, we're adding to international goal, sustainable development. You look at these boxes, and if you look at the second row, affordable and clean energy. Of course, we do that through our work in incorporating new materials with high performance. Economic growth, industry, innovation, and infrastructure, reduced inequalities, sustainable cities and communities, responsible consumption and production. I mean, at least you can say we are contributing to at least 5 of these goals directly through our research. But the most important one, in my opinion, is number 4, is quality education, because we are fortunate in universities when we do research, it's not only the research outcome that matters and its implementation, but the students who get involved in it, and we train them to go to the world and contribute beyond even what we train them for or what we even sometimes imagine. So I want to just remind everybody that whatever I'm going to present and what we do, and I know my colleagues at Illinois and Texas and many universities contribute to these goals. So we have to keep this in the big picture in mind. As you all know, there has been, even for 3-4 decades, big emphasis on sustainability. And I like to say, it's not a matter of being good citizen sustainability. It's actually now, it's part of our genes that we must think in sustainable terms. We must work to preserve the resources we have for future generation. And I think I would be right to say that the current generation and the future generation are even more concerned about sustainability, maybe even more than previous generations. And we see this affecting our community in adopting crumb rubber, RAB, warm mix, plastic modified asphalt. This publication is the recent publication that we issued from our group on plastic modified asphalt. So the question is then remains, how do we do all this, achieve sustainability, but based on fundamental properties and modeling? So what I'm going to present today is what tools do we have, what opportunities we have, and what limitations remain for us to achieve this sustainability based on fundamental properties and modeling, not only based on an empirical observations. Although empirical observations, they have their own value, don't get me wrong. They do have their own value. But if we go to the fundamental property, then we accelerate the technology much faster. So that's what the takeaway, the main takeaway is, how do we do this? And the presentation I want to give on using atomic force microscopy for achieving that, which is providing fundamental approach to sustainability, achieving sustainability in material design. And these are the 4 papers. Number 1 and number 3 on the list already online, available. Number 2 and number 4 are in the process. But if you wish, we can provide you these papers. So some of you are familiar with atomic force microscopy. It's a microscopic technique in which you image the microstructure or the nanostructure at such a high resolution, much, much thinner than the human air. In terms of what you can observe, the human air is 100 micron. Here we can do, as you can see in this resolution here, easily we can do 2 micron and sub-micron in the structure. And I want to alert you that when we talk about atomic force microscopy, it's not all the same. The publications out there and the work out there involves various techniques that they differ significantly from each other in terms of capabilities, in terms of limitations, and what they can offer us. Quickly, if you look at the contact mode, basically the probe remains in contact with the surface as it scans the surface like a nano indenter. And the biggest limitation of this contact mode is the fact that you damage the surface as you drag the probe on the surface, or you can damage the probe. Then tapping mode came as a major improvement in which you don't drag it, you're actually oscillating the cantilever, the probe at a resonant frequency. And it added major improvement because you minimize the damage to the surface. It involves, you see a lot of in the literature on phase imaging. Phase imaging, simply put, without going to the complexity of it, there is a drive function and there is a response function when you give the order to the cantilever. So what they use the phase difference between the order and the response, and they use that to differentiate between phases. That is good, but has major limitation. The main limitation of it is the phase that you get, the phase difference, is a result of multiple things that happen at the surface. For example, a sticky but hard surface may give you the same effect as a soft surface. Then you end up concluding that these are the same phase, which is not correct. Then we move to peak force tapping mode, which is you controlling the peak force. You operate the cantilever at much less frequency than resonance. You get better imaging. Then you go to peak force quantitative, which is an improvement over the peak force. The advantage of this peak force quantitative nanomechanical mode that you get quantitative results. Now we're talking about getting modulus, getting even complex modulus, as I'll show in the next one. You get adhesion, deformation. So you are doing mechanical testing at such a small scale without direct contact, without continuous contact with the surface. And the latest development that we just used recently, and I think we are the first to use it in Asphalt, I believe. I hope I'm not wrong, but that's what I think, is NDMA, the work of Mohammed al-Jarrah, who just recently submitted his work, his paper on this topic, which is NDMA, is a new development from Bruker on doing literally viscoelastic analysis of the subcomponents of the surface of asphalt. That's what we did, and I'll show you some results. So this is how it works in the tapping mode. Each pulse, you approach the surface. This is where the contact started at B. You load it. You reach the set force, maximum force. So now that's a force distance. So now you can calculate modulus, you can calculate energy, you can calculate dissipation energy, and adhesion. Why we call it adhesion? As you start retracting from the maximum force going down, you are actually moved beyond the 0 point. because the material will stick to the probe and drag it with it up. When it separates, that is the adhesion force. So look how much amount of information you get from each pulse, from each application of load. Amazing amount of results. You get heights, you get modulus, deformation, adhesion. What do we do with it? We get beautiful images from it. And I noticed my students and collaborators, they call these shapes depending on the day. Sometimes it depends on your mood, on your background. Some people call it leaves and flowers. Some call it needles and nails. It depends on how you feel about the work. But of course, we're not after pretty images, although they make the day sometimes how pretty they can be and how the design that's created by the microstructure and nanostructure. But of course, that's not our goal. Our goal is to solve engineering problems while we enjoy these pretty pictures. So here is one thing. I'm gonna give you examples of how we addressed really serious technical issues using this technology. The first one is the work of Irena, as referenced below, Holleran. Is the question in New Zealand was they used a lot of porous asphalt, and now they dig it out, and the wrap you get from porous asphalt is different than the wrap you would get from densely graded, because the binder only after 5 years. Look what happened to the PG grade. One PG grade 116, the other one 104. More than you would expect or you do get from conventional. So the question that she wanted to answer is, can I recycle this material? What happens to it when I recycle it? Is it compatible with the new binder? And how do we rejuvenate it? So there are serious technical issues you want to address. And what's interesting, before we go into how we address this issue, that the PG grade of PA1 and PA2 is different, although they were laid around the same time. They are a few months apart, mainly because they use different aggregates. So the porous aggregate, the melter slag, gave more aging to the binder than the gray wake sedimentary rock. So that's what's attributed to. And there is something interesting was observed in this research. If you done AFM, people refer to what's called the B structure. And this B structure exists in the non-associated part of the material. Because when you get the asphalt in the AFM, you see mainly two phases. One is the associated polar molecular associated phase, which looks like connected islands or connected networks sometimes, and sometimes not connected. And you see around them non-polar matrix. So you can see polar matrix around non-polar matrix. But what's interesting, that this B structure that many people have been wondering what it is, we observed it, Irena observed it in this work in the associated structure, which was surprising because usually it appears in the multi-non-associated phase. So we wanted to explain how do these B structures show up in the associated phase, polar associated phase, and what do they mean? Again, we're going to answer a question about the effect of rejuvenators and the effect of the association or polar association and how that impacts recycling of wrap. So this is example of what happens to the structure for one of the mixes, the PA1. So in this case, what you observe right away, by the way, in this case, on all these images, lighter color is a higher value. So if you look at the associated, polar associated zones, they become less and less as you rejuvenate. The modulus of these materials, their modulus become higher, their values, but the material itself became smaller. These associated zones broke down. And it turned out later, I'll show in a couple of slides, that the size of these polar associations turned out to carry a lot of information about the effect of the rejuvenator. And look at adhesion. These associated, polar associated domains, agglomerations, also they have less adhesion. So they are higher modulus, less adhesion phase. And this is revealing information. This is the modulus from the nano indenter, or from AFM. As you can see, as you put more and more rejuvenating, you get less modulus. No surprise. Of course, you would expect this. There's no new information here. But what's new, that one of the materials, PA1, requires 5% more rejuvenating than PA2. So that was an important finding. How much do I add rejuvenator to get for these two materials to behave the same? So they are not the same. You cannot treat the material that came from PA1, PA2. So the first thing we learned from AFM, how much rejuvenator I need to add for these two materials to behave similarly in terms of the modulus. That's not the end of the story. I think this slide here is the most important finding was from this study. Please observe what happens to the PA1 blue bars and what happened to the red bars. So the blue bars, it took 15% for the modulus, for the domain size of the polar associations to stabilize. So look, it reached this value and then this value and stable. While PA2 is stabilized sooner. If you compare this with this image, there's something interesting comes out of it. While the size of the associated group stabilized, the modulus continued to drop. So what happens, the rejuvenator dispersed the associated polar associations up to a limit. Adding more rejuvenator after this limit is just waste of the rejuvenator. Adding more rejuvenating after that point, although you are reducing the modulus, it's not a permanent change in the material. I will repeat. So the finding out of this is how much rejuvenator we used nano characterization using AFM to answer an important question, which is how much rejuvenator I need to add and what does it do? It turned out to be some percentage of rejuvenator is enough to disperse the molecular associations up to a limit. After that, you are just making the nonpolar component softer and softer, which is not something you want to do. You just want to add enough for this polar association to be stable, and that's it. This, you cannot get this answer from doing DSR. And then, so the picture, and then if you look at the paper, one of the nice things we did in this work is we explained asphalt chemistry with rheology through this nano observations. Basically what happens, you start with these polar associations, and as you age the material in the field, you get larger polar associations, which is known, and then you get these B structures dispersed in the non-polar zone matrix, but you trap some of these B structure inside the polar associated groups, which is a new observation. In fact, when we observed, when Irina did this work and observed the binder, she did not find this B structure inside the associated groups till she waited 14 days. And this has to do with the asphalt association continue to grow to reach thermodynamically stable point. Now, for the material wants to reach the lowest energy possible. For that to happen, to reach the lowest energy possible, what it has to do, there will be this zone, which is less polar, that's wax, than this, or non-polar, compared to the polar group, so it creates an interface. Our thinking is that this polar phase squeeze this wax and make it triple, that's why it looks like this V structure. And you can see it in the AFM. So AFM corroborated the chemistry model, which I think is very, very important to explain chemistry through these observations. When you add a rejuvenator, two things happen. One is you disperse, you improve, hopefully improve the dispersing properties of the continuous phase. So you let these associated groups disperse even more, and you overcome the polar contacts or polar bonding, which are weak bonds, hydrogen bonds and van der Waal. Inside, you make it smaller and smaller and smaller. Any more rejuvenating you add that does not make these smaller does not add value to the rejuvenating. It's just temporary value that has no, or does not add value to the performance of the material. So my point is, we were able to explain the asphalt chemistry with this paper, the model, and what happens to these polar association, non-polar groups, and what does it mean to performance, and what does the rejuvenator. And the key message is you don't want the rejuvenator to make a permanent softening of the binder, because that means you will end up having problems with rotting. You want it to rejuvenate it enough to resemble the unaged binder, but you don't want it to be a permanent effect on softening the matrix. This is the work of Amal, switching to Amal work. Amal, and this collaboration, of course, with my dear colleague, Dr. Ebs Martin and Edith Arambula and Fawaz Qasir. They did this work for NCHRP, and we just contributed to the AFM work late in their project, in which Amal looked at different groups of rejuvenator, different groups, different RAB groups. This percentage here, 31%. This is the percentage of RAB. And she looked at what's the effect of adding different percentage of a rejuvenator. And I don't want to go into all the details of her work, but it's simply, her results actually similar in many ways to the results of Irina, but there is an interesting thing in her work, which is this. And this can be used as an index or a method for assessing compatibility between in the binder when you add rejuvenator. So this is the material with 31% RAB. And this is with 31% RAB, but 1.2% rejuvenator, and this 5.5. What you observe is the bimodal distribution. As you rejuvenate it, become more normal distribution instead of being bimodal. This change can be also helpful for practitioners. If we use AFM, we can tell how much rejuvenator is needed to create that, remove that bimodal distribution, and also to address how much of it we add and how effective it is. So simply put, we can use AFM to get such information that tells us about the effectiveness of the rejuvenator. This work done by Lakshmi that looked at how does the modulus increase as you put more and more RAB material. And to our surprise, I mean, in DSR, if you run dynamic shear rheometer, you see that adding RAB affects the modulus quite a lot. Here we showed that even adding 35% RAB, the modulus increased, of course, but not to the extent that's reported by DSR. And maybe I can argue, and this is point for more research, that's why RAB works very well, because it does not affect the fundamental, at the fundamental level, the nano level, as we would think by doing DSR. In fact, here are the results. These are DSR results, and if you look at the coefficients 0.04, 0.05, and if you look at the AFM 0.02, the adding RAB binder to virgin binder does not increase the stiffness as much as one sees in the DSR. So maybe the DSR is just pick up the dynamic shear rheometer too much of a stiffening of the RAB that really does not happen in the nano level. Okay, switching to something very exciting. Recently, we did this work. All the results I showed you before is done assuming that you measure one modulus at a certain frequency, so it's like quasi-elastic material. What I want to show you in the next few slides is measuring true viscoelastic properties of the binder, dynamic modulus phase angle at the nanoscale, at different temperatures. Huge opportunities are open, so you can zoom in at any phase you wish, any point you want in the microstructure, and you can get the dynamic modulus as you would do in dynamic sherriometer as a function of frequency. You can get that, this, for example, this work that Muhammad did is for including plastics. And we were using it to see how compatible that asphalt with the plastics we're adding and with the additives. You cannot get this information from other macroscopic tool, because now he can zoom in at this point and say, look, my plastic is still there. It did not melt. It did not do any homogeneous mixing with the binder. So you can get a huge value, tremendous information about the compatibility between the material you're adding and the binder. And not only this is so exciting, you can get the viscoelastic properties at the nanoscale. Here is the G star. We did this at 25, 35, 45 degree temperatures, multiple frequencies. We shifted the data as you would do in time when we shift viscoelastic properties. So this is the G star. And you can see the observation. Of course, this is not surprise that the dynamic modulus from the nano characterization is higher than the macro. You can get the delta. So the material has, at nanoscale, is less viscous than you would get in the bulk. And it's easy to explain that because there is no much slipping at the nanoscale as you'd get at the macro scale. And you can get even the time temperature dependency of the material. So you can get full characterization of viscoelastic properties of the material and its components. I think that's very exciting. I think this will open the door for characterizing homogeneity of asphalt at nanoscale, you measuring these viscoelastic properties. I'm gonna just quickly go over and then open for questions. Another technique, I talked about AFM, I'll talk about low field NMR. This is not the classical NMR high energy, high frequency, 600 megahertz that you would use to get information about the composition of the binder. This is low field NMR, and it's used by petroleum engineers use it to get information about the viscosity of the fluids in the cores. And Ilaria, who worked with us in Qatar, did this work with other collaborators to look at, the question is, can we use this technique to characterize aging of asphalt in situ? What I mean in situ, not in the field yet, but without extracting the asphalt. So how do we measure aging of asphalt now? We extract it from the mix. This intends for you to put a core in the nuclear, in the NMR at 2 megahertz, not that traditional 600 megahertz ones that you get the composition that we do in chemistry. 2 megahertz, low field NMR, and you observe parameters of the decay of the signal. And that decay of the signal is related to the new hydrogen nuclei in the sample. And from that, people have shown that you can relate two indices, one called the relative hydrogen index, and the other one is the relaxation time. Those two are related to the viscosity of the liquid in the material. In our case, that liquid is asphalt. So the thing is, I can get the viscosity of the asphalt whilst the asphalt is in the core. So no extraction. Can I get the viscosity of the asphalt while it's still in the core, no extraction? And this is some of the results that shows promising results, where we looked at viscosity in situ in the core for unaged RTFO aged and PF aged, and indeed the technique was able to show the effect of aging on the viscosity without extracting the binder. This is another experiment we did with Dr. Okan Serene. We did it in Qatar University. We looked at various groups where they aged it in the oven for different parts, and our results was showing that we can pick up the aging of the binder in the core. It's great because we don't have to extract the binder. It's still limited because I have to do it in the lab. I cannot do it in the field. This was an interesting one, back to aging and back to RAB. This was done with the collaboration with Dr. Epps Martin, where we took a virgin binder, we did the RHI, and this was, by the way, blind testing. We did not know which one is which when Ilaria did it. And we showed that the virgin binder has, and the RAB has much lower RHI. RHI means higher viscosity binder, so that's great. And when we put the rejuvenator, it showed that you went back to the original binder. That was good, but there was a surprise. Here's the surprise. When we took the material that showed that the rejuvenator worked and brought the RHI to the original binder level, we put it in the oven, that particular rejuvenator lost its effect. So it had a temporary benefit in softening the material. And I want to link this to what I talked about AFM. Remember when I mentioned about AFM, when you add the rejuvenator, the reduction in stiffness cannot be your only indication of quality of the rejuvenator. In fact, looking at what happens to the polar associations and reaching stable level can give you much better indication if this rejuvenator continues to work or it stops to work at a certain level. Imagine if I take this same material, put it under conditioning in the lab, under aging, and then come back and look at what happens to it in the AFM and what happens to it to a device like low field NMR to answer the question, does the rejuvenator remain effective or it was only a temporary effect? So we can answer it with these techniques. So in summary, we had in Sharp, we made a huge jump between quite crude empirical test called penetration test that has no scientific value whatsoever, but was useful in many ways, in some ways, to completely linear viscoelasticity, and then we went to nonlinear viscoelasticity when we adopted the MSCR, multiple stress creep recovery test, to even damage testing. So we made a huge jump from this domain to this domain. And I think we can do a similar, and we use that scientific method to now label binders and group them and grade them. And it's not out of question that we can, maybe not long time from now, use these techniques to help us even more and more, not only help, but also to characterize binders. And I dare to say maybe even to grade binders, or grade rejuvenators, or grade RAB, by looking at what happens to the nanostructure. As I showed you, now you can do this test here. You can do oscillation test, get G star and delta at every point in this binder. And also, as I mentioned, we get these pretty images, and they are really pretty. I mean, look at this. This is like leaves and flowers, and you look all kind of geometry. But when you look at these images as engineers, what we see also, we see data. Huge amount of data. Huge amount of data, modulus, dissipation, and interrelated data, correlated data. This shape does not happen except there's correlation in the properties and they associate. So we see huge amount of data. So that's important to see. And currently, whatever I presented cannot even start to scratch the surface of using this data. Whatever parameter we came up with, whether the normal distribution, the histogram, do this, that still gets useful, but it's not enough. We can extract a lot of data. We have a big meal here, and we're only touching the appetizer. So the achievements, we can use these such tools, nano tools, to design and analyze sustainable asphaltic materials. They offer amazing opportunity to understand the chemistry related to rheological properties. We are able to measure dynamic viscoelastic properties at nanoscale. So now you can look at compatibility of materials. You can design these materials to be much more effective. What are the opportunities? The opportunities that we generate a huge amount of data about properties, phases, topography. There's an opportunity now with AI, artificial intelligence, deep learning, to analyze this big data and combine it with fundamental properties and chemistry. But there's challenges. The challenges are that in our community, none of these tests are standardized. So I think there's an opportunity and a challenge for us to standardize the test in terms of how it's done, how do you do the test, what forces you use, depends on the scale of binders we work with. There's a lot of issues to be addressed there. And then once you standardize these tests, let's do it in a consistent way on large sets of materials under various conditions. So we generate that data that will help us to go beyond just scratching the surface and using typical parameters to analyze the data. So these are the achievements, opportunities, and challenges that I think are happening, giving this opportunity. With that, that's the end of my presentation. And Isaac, back to you to see if we have questions.
Thank you so much, Professor, for this very interesting presentation. We do have some questions now in the chat. And again, if anybody wants to ask this question, they can raise their hand and I can give them the floor to ask the question. One of the questions that came up in the chat is how representative are nanoscale AFM images of the binder to the macro properties of the binder?
Very nice. You know, actually, excellent question. It's at the end of the day, that's what I mean by standardizing the method. Is how do you get enough images that you are representative of it, representative of the macro scale, and how do you image it? Do you image it randomly or do you image it in pattern? So that is important to address, but has not been so critical. I think it does represent the nano. Our materials are uniform at, relatively uniform at the nanostructure, but we still need to uniform in terms of sampling. But still we need to do better job in designing an experiment that ensures that these measurements represent the macro structure or the macro performance, not the macro properties necessarily, because the nano properties and macro properties are expected to be different. They may correlate, they will correlate, but they can be different too.
There is another question, which is the model's value are dependent on the peak force set point and the spring constant of the probes. If we vary any of these parameters, then the values are expected to change. How reproducible the results are?
If we standardize it, they are reproducible. If we don't, they are not. That's why I mentioned again at the end that you need to standardize it. But there is, like, it depends on the method. That's why it's hard for me to take images from another group and say I can correlate it to what I've done because of the same exact reason this question was asked. So you need to make a standard of how do you calibrate. So for Bruker, for example, there is relative calibration based on a material with no modulus, you calibrate it, or you do the absolute calibration and they have a method for it. How do you do the absolute calibration? Like in the results we did with the first study I gave, Arena, we chose to, we did vary the force, but we tried to keep the indentation or the amplitude constant, because you cannot look at the values. The values were from 5,000 megapascal to hundreds megapascal, so you cannot use the same force. Otherwise, you end up penetrating in one location much smaller than the other location, and the results cannot be compared. So in our case, they all were in the same range of indentation or amplitude of the deformation, but the forces were different. So back to the point, yes, they need to be standardized in order to be globally interpreted, the results.
Thank you. There is also another very interesting question in the chat, which is, whenever you were showing the results of the different percentages of rejuvenation, they were asking about how the images were taken so that you can have apple-to-apple comparison, and how they were standardized or how they were taken in order to make sure that they are you're looking at the same thing.
Yeah, that's back to the calibration of the method. So, as I mentioned, to calibrate based on having all the images are within the same range of deflection, but the forces are different in our case. That's how we compare them.
Thank you. Another question: how do we know that the dispersed phase is the polar phase? What was the AFM Pro properties for NDMA?
Say that question again, Isaac, please.
So the first part is, how do we know that the dispersed phase is the polar phase? And the second one is, what is the AFM Pro properties of the NDMA?
On the first one, how do we know it is? We did not extract it to test it whether it's polar or not, but can be done. You can do also chemical probing by putting functionalized group at the tip, and you can check if they are polarized. This was concluded, as we explained in the paper, by observation, by looking at what happens to this material as you add aging. For example, why this polarized polar to polar associations happen, because of the van der Waals and the van der Waals forces, and because of the hydrogen bonds in these groups, as well as because of the heteroatoms and the that is also functionalized and create bonding. When do these things become more significant? As you age the material, if you add RAP. So it's easy to observe that as the material is more aged, you see more of these agglomerations. So we inferred that these are the polarized groups. And we explained in the paper how we came to the conclusion that this is a polar associated groups, but we did not extract it to test it if it is the polar associated groups. So it's by inferring from the results that it is. The second one, the technical, that has to be a question to Muhammad al-Jarrah. We take the question and I will send you the answer, Isaac, about what is the exact characteristics of the probe used in the, it's explained in his paper, but it's not available publicly yet.
Okay, thank you so much. We have a long list of questions. I'm trying to go over them quickly. There is one question that is asking about the rejuvenator binder that was aged. What was specifically in the modifier that made the difference in the results?
Can you tell me which slide, or I'll say the question, maybe I can get...
Javier, can you please ask your question?
Thank you.
Javier? I think he wrote this question. I'll just
say it again, Isaac. We'll see if I can answer it, and then say it again, please.
So he's asking about the rejuvenator binder that were later aged. He said, can we know what in the modifier made the difference? So maybe what he means is what specifically component of the modifier that is making a difference in the result.
Okay, so it's not the modifier. So when you add the rejuvenator, our hypothesis is it works by doing two things. One is overcoming the polar to polar bonds So it makes the polar associations break and become smaller. Not only this, in fact, what's interesting, they don't only become smaller, but they change shape to become not spherical, going towards spherical, which is because the spherical shape is the most thermodynamically stable shape. So that works by that mechanism. The second mechanism it works by is by improving the dispersing properties of the continuous phase around them. Now, what we are saying, and this is also still a research point, the rejuvenator will make these polar associated groups smaller. They will change their shape, okay? But adding more and more to it without affecting these associated groups is just not useful. It makes the continuous phase softer and softer and softer, which is not something you want. So why keep adding that rejuvenator? The bottom line is we think that this explanation will help you to choose the type of rejuvenator that works truly in changing the material and does not add complexity, because the rejuvenator at the end is a chemical, right? So how about if this rejuvenator has an aging characteristic that's even worse than your binder? So you're adding a problem instead of adding a solution. Now I'm saying that by doing DMA, by doing AFM, we can subject that mix of rejuvenator with binder to multi-experiments in the lab and test it to see what happens to it, instead of claiming that just softening the binder is a rejuvenating process.
Thank you,
I know Dr. Wala Mugawar is listening, and he's done a lot of excellent work on rejuvenators, and he has a lot of practical experience with it. And I remember discussing with him that it's not only many things that can do softening does not mean it rejuvenated the binder. And that's what I'm saying from the AFM observation.
Professor, there is also another question that is asking about the rejuvenator type. Somebody is asking if you did or are you planning to test different types of rejuvenators, such as like bio-based versus aromatic and...
Yeah, I know the work that's done in Illinois on this last TRB. Dr. Hassan Ozer presented this work. We can do it. I have not done it. The ones we evaluated are bio-based. But we have not looked at the various. But I believe that doing the AFM, and I encourage those who are doing it to look at the paper by Holleran and by Amal when it's out, to see if you can build on it and to see if you can confirm what we're saying when you add aromatic and other types of rejuvenators, and see how does it change these associated and unassociated groups.
There is a question that is asking about the first paper that you mentioned. Somebody is asking what are the types of the binder that were used in there, and what was the technique for the long-term aging? Was it through PAV? And they ask if you can please share the papers, or at least the titles of the papers.
Yeah, the paper it's in my presentation, Isaac, so feel free to share it, or I'll share it with you. So the binders were SBS modified binder originally when they were put on the road 5-6 years ago. So they are originally modified binders. When Irina did this work, which is part of her PhD in Auckland University, by the way, she followed the ASHTO method, where the RAB material is not PAV aged anymore. You don't PAV age it in the lab. You characterize it because it's already aged. So all the results are done on RT4 aged binder. When I say RT4 aged, it's already aged, right? It's been 6 years on the road. So we did not age it further in the lab, but it's SBS modified binder.
Puneet, can you hear me?
Yes.
If you want to ask your questions, I read you had many, so please feel free to ask them.
Okay. Professor Masad, thank you so much for such an informative presentation. I have a couple of questions, and maybe like some are very basic. Like, how are you defining, let's say, rejuvenator? Is it based on chemistry, or is it based on, like, what is the basis of, let's say, differentiating a modifier as rejuvenator, or let's say a softener or anything? That was my
No, I
first
did not.
question.
Excellent
Yeah.
question. No, I did not define it. I was just told that this is a rejuvenator, so I called it a rejuvenator.
Okay.
But now what I'm saying, in fact, what I'm saying that we need to, I think you're saying the same thing or alluding the same thing. We need to go back and say what's truly a rejuvenator.
Yes.
And I'm saying that we have the tools now to differentiate simply a softener that keeps softening the material from a true rejuvenator that changes this, that makes a change in the material in terms of these polar associations.
Okay. And my follow-up question was, like, for example, in the AFM, you showed different polar phases. So is there any chemical analysis, like any sort of SARA method, which you perform to validate, like, whether those polar phases are chemically accurate, or it's based on the AFM results only?
Dr. Epps Martin and her group use SARA AD analysis. It's available on these binders. And we Amal looking at the results of the SARA AD with the AFM correlation. But I think to do the SARA AD, at the end of the day, the SARA AD, the 4 fractions you do, it will not prove or disprove, I think, what we're doing, because at the end it's gonna tell you bulk. Yes, there is asphaltene, there is aromatics, there is resin and saturates, but does not tell you that what I saw in the AFM is which one is which. You know what I mean? You have to do it in situ as you image it and test it, know what material it is.
Okay.
But by the way, there is a question earlier, and the same question you asked. The dissipation test, the dissipation can give you an idea about whether it is polar or non-polar. Not directly, indirectly, whether it's dissipation. So the wax material had higher energy dissipation, or what we called it wax, because we claimed that because it's non-polar component. So you can qualitatively correlate the two.
So was something like this performed as part of this study, or which we can refer to, or something like that, or was it not done as of now? Like some sort of comparison is done already?
In the work.
Okay. And sorry, I have one more question. So you mentioned about low field NMR, and the plots was showing that as you age the binder, you see that there's an increase in viscosity happening. So I was wondering that does it have any impact on the aggregates, because you measured that in the core, like field.
Wonderful question, Puneet. This method completely blind to the aggregate.
Okay.
Completely. Because it really actually does not even see the aggregate. So whatever aggregate, unless it has magnetic properties, it will not interfere. So I used, if you have proper aggregate with magnetic properties, it will interfere. But in terms of viscosity, it's blind to it. It's not going to see it.
Okay. If anybody has an additional question, otherwise I'll go ahead and ask maybe another question. I'm sorry. If anybody else has a question.
I don't think...
You can always email me, and I will be happy to answer, or send you to my students who will answer better than me in this respect.
Sure, Professor. So if Isaac, if we have time for one more question, and if nobody's asking,
I don't think we have time for more questions.
Okay. Fine. Thank you.
I'm sorry about that. Thank you so much, Professor Iyad Masad, for this very nice presentation. And from the question, you can feel how much people were engaged in your presentation. Thank you so much for sharing this information and giving us from your time. And that's it. Thank you so much.
Thank you all, and God bless you. Stay safe. Thanks for my colleagues who are listening, and to all of you, Imad, Wala, I hope to see you in Doha, inshallah, and enjoy your company again. I'm sure there are other names. I cannot see everybody on the screen, but if you're flying through Doha, stop by, okay?
Thanks, Iyad.
Here is Camila too, writing, Sayyida. Wow, I'm meeting a lot of friends here. Thank you.